All right, let's get started with section 4.3 about optimization and modeling. This is a difficult section. This is one of the more difficult sections in the book. I think we might take extra time to go over it for 2 days in class. Uh, I'll try to do a lot of examples of it here. But for now, what you need to know about it is that it involves real word problems, the kind of word problems that you had in like Algebra 2, where you had to make up your own equations to describe stuff according to certain formulas. There's a lot of important formulas out there, like the area of a circle, for example, is pi times the radius squared. You know that its circumference is 2 pi r. Things about spheres, the volume of a sphere is 4/3 pi r cubed, and its surface area is 4 pi r squared. And there's the Pythagorean theorem that you use all the time. So, for example, if you have a right triangle where this length is A and this length here is B, then the hypotenuse obeys, if this is C, and it's a right triangle, obeys the Pythagorean theorem. A squared plus B squared is always going to be equal to C squared. Things like that. So the kinds of problems where you have to set up equations to describe stuff and then be a little creative with it, which was one of the harder things about intermediate algebra. But it's also, I think, one of the absolutely most important things in math in general is to do kinds of word problems like this, because math on its own, if you're like an engineer or a scientist and you're good at solving equations, but you just have the math on its own, but you're not good at like describing the world with math, and you're not good at interpreting math in the context of real world problems and being a little creative with it, it doesn't matter how good you are at solving equations. So it's worth struggling with, spending some time with. So both of these problems are a little tricky. Maybe not that tricky, but if you get stuck on them, that's okay. Spend at least 5 minutes struggling if you don't get it right away, is your goal. And then I'll show you the answers after you've paused it and tried it, and we'll do some more examples of how this applies to calculus in a few minutes. So that will be in 3, 2, 1. All right, here's what I got. This area is 1/2 times pi times the quantity p over pi plus 2 squared. It might come out differently if you used a different method, but it should be more or less equivalent to this. I just realized as I was doing this that warm-up number 1 was harder than warm-up number 2, so sorry about that if you got stuck on number 1. But anyways, that's how that one works out. The perimeter, the distance all the way around, I'll explain this, is the 2 pi r here, that's the circumference of the entire circle. But we don't have the entire circle. This is actually only half the circle, which is why we divided this by 2. And so that pi r part of it is this part of the circle. And then the plus 2r is, there's a r here, that's the radius, and an r here, and that is that part of it. So then the trick is to get this thing that it's looking for, the area in terms of its perimeter. That means that A should be the output variable in the equation, and the perimeter should be the input variable. That means that we need to get this. We have these two equations that are both in terms of r, but it's not for a in terms of p. So we actually need to actually solve this equation for r in terms of p, like so. And then once you have this formula for r in terms of p, you can then plug that into the r in the formula for area. That gives the area like you want here. So that one was pretty hard. Warm-up number 2 is maybe not that bad, sort of a basic kind of trigonometry thing. But this is how it works out. There's the distance 20 plus the distance across the field, which is the hypotenuse of that triangle. And so this distance comes out to 80 here. A is 80 because it's the total distance of 100 minus 20. B is 50, and so the hypotenuse of that triangle is the square root of 80 squared plus 50 squared, and that comes out to be 114.3. And this is actually an example of the kind of optimization problem that we see in this chapter, where if you imagine that this is a real life situation you might have been in before, where imagine like there's kind of high grass on the field, and it takes like a lot of energy to walk through it, and you don't want to go straight across the field. That would be the shortest distance because it takes more energy to walk through these weeds and high grasses or whatever. And you can walk faster on the sidewalk on the side. So, but you don't want to go all the way around. So like but you want to go as fast as you can. Maybe you're running a race or something. So like, what is the optimum point to start cutting across? Like maybe it depends on how bad the weeds are and how much slower you go there. But the optimum point might be over here, where it's almost the shortest distance, but most of the distance is through the field. Or maybe you're just going to cut off a little bit, depending on the situation. So that's an example of when we need to optimize something like the time it takes to go across by adjusting what point you go across. So anyways, so those were some hard problems. So excellent work if you did those. Let's look at an example and then go also through the method of how to do examples of these optimization problems. So this is sort of a classic example that you can maybe picture. So let's say you're a can designer. You got a job as a can designer working for a juice maker, I don't know, and you need to design a can. Your boss told you we need a can that holds 40 cubic inches of juice, and so that's the volume of the can, how much liquid fits in it, and we want to use the least material. The material is on the outside of a can, and so we just need to make it so we use like the least aluminum, which we're going to say the surface area is equal to the amount of aluminum you use, because it's like cut out of a sheet, basically. So that surface area we want to make as small as possible. And yeah, we're making a cylindrical can that's capped on both ends. So let's see, like you can imagine a couple extremes here. Like if you make a can with a very small radius, then it's going to have to be very long. So here the radius is small, but the height of it, we'll call it, is long. But then here's another cylindrical can where the radius is large, but then to keep it so it has the same volume, so you can imagine maybe these have the same volume, you end up with a small height. And both of these are kind of extremes. Like you've never seen a can in the store in this shape for a reason, because it's a waste of aluminum. And there's some point in between where it's ideal, but it's not clear where that is. Is it more like a soda can, or is it more like a can of tuna that's flatter? Like what is the most efficient can? So the way we're going to solve this is by following this general method. And the first thing to do is just make sure you've read it and understand it. I didn't write that down. Read it carefully, maybe twice or 3 times, depending on how sleepy you are. If you're sleepy, you might need to read it 4 times. Like I'm kind of sleepy right now trying to make this video. But anyways, let's start by trying to identify the quantity, the output of the function to be minimized or maximized, and see what variables can be manipulated. So in this case, the output we want to optimize, and optimize is just a term for either minimizing or maximizing, depending on what you want to do and depending on the context. So in this case, we want to optimize the surface area, but no, I don't want to just say optimize. We want to minimize the surface area. And what variables can we manipulate? The variables are r and h, the radius and the height of the can. And at this point, that's sort of the easy part, but it is important to know what is the variable you want to minimize and what are the variables that you can change. Because the goal here is to get an equation of this form, area as a function of just one variable, like f of r, or maybe some function of the height. It could probably be either one, with just one variable in it. And that's easier said than done. This is one of the harder things in math, like I was saying before, is to figure out how to do that. And it's a thing that there's a lot of tricks to it, and there's a lot of skills, and there's a lot of techniques. And you got through an algebra class, so you already know a lot of these. So you're going to have to remember all that stuff. So at this point, this is where we might have to use our imagination, draw some pictures. I already drew some pictures here. Write equations that relate to all of these quantities that we have here. So you also want to see what is fixed, like what is given in the problem. That's the volume. The volume is going to be a constant, specifically the constant number 40 inches cubed. And so all of these things that we have here, we want, just think of all of the equations that relate to area and all of that stuff. So one thing we need to know about is the area of a circle, because it looks like we have two circles, the tops and bottoms. So let's start by writing some of those equations. Of the circle, so the area of a circle is pi r squared. This one has two circles, so our area, our surface area that we're looking for is going to be pi r squared plus the area from the sides. So that's the top and bottom, and there's two pi r squared, I meant to say. Pi r squared for the top and pi r squared for the bottom. I forgot the 2 again. And there's also the side. So let's figure out what the side is. So to get what the area of the side of this cylinder thing is, the trick is to realize that it's actually essentially a rectangle. Because if you were to like take the cylinder and let's say slice the cylinder on like right here, so this is only the side part, and like essentially unwrap it like this, and it will turn into a rectangle if you flatten it all the way out. And so let's see, what is the length and width of this rectangle? Well, the height is going to be, well, that's just what we're calling h here. whatever that is, and then the this distance here, the length of it is the circumference of the circle, because the circumference is 2 pi r, remember? So it's the circumference of the circle because that distance from there to there was previously wrapped around the edge of the circle. So that's the length of this, is 2 pi r. So the area of a rectangle is its length, 2 pi r, times its width, which is 8 h in this case. So this is good. This is now an equation that gives you the thing that we need as the output, and but the problem is it has two variables in it. It still has the h in it. So what we're going to do eventually, the goal is to minimize this equation using the 4.1 methods, and those methods in 4.1 and 4.2 are essentially find the derivative of the area with respect to one of the variables, let's say r, and set it equal to 0 and see what is the value of r that makes that 0, or what makes it undefined, or what makes it some other kind of minimum or maximum. So to do that, we're gonna have to turn this into a one variable equation so that we can actually take the derivative of it, because if it has an r and an h in it, that's not quite gonna work. So how can we do that? Let's get a formula that relates h and r. How can we relate h and r? And you're gonna get stuck with these things a lot. Maybe one thing to do if you're stuck on a word problem is to look around for things you haven't used yet. What kind of information have we not used? Oh, here's some information we haven't used. The fact that the volume is a constant. And the formula for the volume is going to relate r and h. I'll give you the formula, and then I also want to talk about it real quick. The formula is pi r squared times h, and there's a lot of things that have the same kind of thing, where if you take the area of one side, of like the top or bottom in this case, of the circle, and multiply it by the thickness of the thing, in this case h, you get that formula. And this doesn't just work for circles. If you take any weird shape like that and just give it so it has some area here, and then you take this shape and turn it into a three-dimensional thing and give it some depth, and that just ends up looking like that, you can still get the volume by doing the area of it times the height, and that works for all kinds of different shapes, as long as the sides are straight up and down at a right angle to the thing, which this one isn't quite because I didn't draw it very well. But anyways, if you have this formula here, pi r squared h, and we know that this is equal to 40, then we can actually solve this equation for the height in terms of in terms of r, like so. This will become h equals 40 over pi r squared, and then plug that into this h here. So this will become 2 pi r squared plus 2 pi r times 40 over pi r squared, and one of those r's is going to cancel out here, one in the top and the bottom of that fraction. So we actually end up with this formula. So this is what the goal with all of these problems, all these optimization problems should look like, is write an equation for the thing to optimized in terms of one variable. And once you've got that, we can get the derivative of it, set the derivative equal to 0, see where the derivative is undefined, think about endpoints of this. By the way, we haven't talked about the domain of this. It's usually important to think about the domain. One thing you notice here is that 0 to the negative 1 is undefined, so you're not allowed to plug in r equals 0. And other than that, the sky's the limit. I mean, I guess you could have a super, super thin can that's like 100 feet tall or something. So I don't really know what the upper limit would be. Maybe the upper limit is like the radius has to be more than the thickness of the aluminum, or it can't hold any liquid. I don't know. But anyways, the domain is going to be essentially that r must be between 0 and infinity. R can't be negative because you can't have a negative radius of a cylinder. It doesn't really make physical sense. So anyways, we're going to get the derivative of this. Let's just call it area. And that derivative with respect to r is going to be 4 pi r to the power 1 minus 80 r to the negative 2. And we want to know where is this 0 or undefined. This only undefined if r is 0, and that's not in the domain of the original one anyways. So I'm just going to set the output of this to be 0, and this is going to look like, how can we solve this? Well, one thing to do is to try to factor it. You can factor a 4 out. Also, I don't like this r to the negative 2 in there. Maybe let's multiply everything here by, let's say, r squared to cancel out with that. And then when that gets distributed in here, it will cancel out with that, and you'll end up with r squared times this other one. And then we'll solve this equation. So you just get r is the cube root of 20 over pi, or as I like to call them, 20 pyths, and that is about 1.85 inches. And maybe that sounds reasonable if we're talking about the radius of a thing. I guess a radius of a can. I guess that means the total diameter would be like 3.5 inches, which sounds like a reasonable can. Let's just think a little bit about the domain of this and what the graph is like, just to make sure that this is actually the optimum and not just this is a critical point that we found, but we want to make sure that it really is the minimum and not just like either a maximum. So that's a critical point. But let's think about what the graph of this is going to look like if we do that radius versus area here. Thinking about the pictures we saw over here, if you've never seen a can with a really small radius like that, because that would take a lot of aluminum for that to work. So if r is close to 0, like that small can, then the r to the negative 1 thing will become large, and so that means the limit as r approaches 0 of a is equal to infinity. So it looks like that on this graph. And out here, the limit as r approaches infinity of a as we go out this way, well, in that case, the r to the negative 1 is going to approach 0, but then the 2 pi r squared, that 2 pi r squared that was weird. That is going to approach infinity this way. So it's going up in that direction and up in this other direction, and it has one critical point in the middle. The only really way this could be shaped is to look like that, and I don't know exactly where it is. Well, I do know exactly where it is. It's at when the radius is the cube root of 20 pyths, also known as 1.85 inches. That gives it the minimum surface area. And maybe you want to tell your boss not only what that should be, but also the height and the area. Those are probably relevant to the discussion. So we're going to plug in this value of r into the h and the surface area as well. And there's those solutions. I took the formula figured out over here for h in terms of r, plugged in 1.853 into that, got h is about 3.71, plugged that into the surface area and got this. I hope I didn't make any mistakes. Maybe I should graph it just to check is a good idea after I spent all that time on this. So let's see what this graph looks like. And this is what I got using GeoGebra here. Whoops, messing around with it a little bit to get the graph to fit. And yeah, it looks like it has a minimum about at 1.85 inches, and that minimum is about 60 something. That sounds reasonable. So that was a doozy. These problems are tough. There's going to be a lot of homework for this section. We'll take some extra time to get through it, and we'll do some more. All right, so here is example 2. I'm not feeling very creative. I'm just copying examples from the book today. So Elena wants to get to the bus stop as quickly as possible. There she is at this point. The bus stop is across this grassy park here, which is 2,000 feet west of where she starts and 600 feet north, and from her starting position here. And Elena can walk west along the edge of the park on the sidewalk where it's faster at 6 feet per second, and she can also travel through the grass in the park, but only at a rate of 4 feet per second because the grass slows her down. And we want to know what path gets her to the bus stop the fastest. At what point should she leave the sidewalk here where she can go a little faster to cut off the corner? And so this is going to have some stuff kind of similar to that warm-up problem we did. And so let's think about the steps that we were doing here. First of all, reading it carefully. And now we want to identify the quantity to be minimized or maximized, and what variables we can manipulate. Draw a picture. I already drew the picture for you. And try stuff with the goal of getting this output in terms of just one input variable, and then take the derivative of that. So she wants to get to the bus stop the fastest, so let's call that the time is the thing to be minimized. And then think about what are the variables. Let's call it x, the point at like the distance she goes before she turns around. So this distance here, so not turns around, I mean cuts across the park. So that distance here, let's call that x. So we want to minimize the time by finding the best x. And the units of this are all in feet, right? So we got that. And then at this point, we know the goal of all this messing around is to get some kind of, let's call it t of x function that gives you the time, or maybe we can write it as, so let's call that t seconds. So we could say t, this output variable, if we don't want to write it as a function, is just some function of x. And that's the goal with all this messing around we have to do. So first of all, let's notice that the distance from here to here is x, And let's think about the time to walk along the sidewalk. So let's just call it t sub side here. And so the time that you go is equal to the distance divided by the speed. That's like saying that distance divided by r is equal to time is the same as saying d equals r times t if you multiply both sides by r. And in this case, on the sidewalk, that distance that you're going is x, and the speed that you're going is 6 miles per hour. And you can just check that the units work out here is always a good idea. Or sorry, not 6 miles per hour, feet per second. So that's that, and then this is x feet there, and then the feet will cancel out, and that gives you x over 6 seconds. The seconds are in the bottom of the bottom. You can bring it to the top. So that's that. And then there's also the distance across this hypotenuse here. So we need to figure that part out, and the goal is to get it in terms of x. Well, first let's figure out what the distance is. We know it's a hypotenuse of a triangle. This one leg over here is 600 feet. This other leg from here to here, that's going to be that total distance 2,000 minus x. And so that means this distance, if you use the Pythagorean theorem here, is going to end up being the diagonal distance, the hypotenuse, is the square root of 600 squared plus 2,000 minus x squared. And so then we can do the same thing to get the time it takes to go across the grass, across the park there. And that's still going to be that distance divided by the speed. But in this case, the distance is that hypotenuse, which is kind of ugly. And that gets divided by that lower speed, which is 4. So if we just add these up, we get the time to walk on the sidewalk plus the time to walk in the park, and that will give us this goal thing that we need. We can write this as 1/6 of x, and then let's simplify this square root stuff here. And on second thought, I can't see a good way to simplify this. It was worth a shot, but maybe the easiest way to write it is just like this. So that's gonna be here. And I just wrote it in this format just because it might be a little easier to take the derivative of it using the power rule this way. The divided by 4 is the 1/4, and I wrote that as to the power 1/2. So now the goal is to find the derivative of this with respect to x, and wherever that is either 0 or at the endpoint of a domain or undefined, it's going to be a critical point of the a place where this might be maximized or minimized. So anyways, this derivative ends up just being 1/6 plus the 1/4 is just a constant multiple, so you can leave that alone. Multiply that by 1/2 and you get 1/8 times the 600 squared plus 2,000 minus x squared to the power negative 1/2. But then we need to use the chain rule here and multiply this whole thing by the derivative of the inside, which is going to be the derivative of 600 squared is 0, plus the derivative of this whole thing is going to be, need to use the chain rule again. uh, and multiplying that by this -1 here. And this looks like a mess. This is the thing we need to set to be 0. And I set that derivative equal to 0. This, by the way, is a really tough problem. I forgot how involved this whole just solving this equation is. This is a tough equation to solve. We could do it by keep solving it, and I'll do that right now, but I'll pause it so you don't have to sit through the whole thing. All right, this is what I got trying to solve this equation. It took me a while. I had to cancel out all of these denominators. I made a mistake somewhere in here. If you can find the mistake for me, I'll give you a high five. I know I made a mistake because the book's answer is they said, oh, we can find the critical points analytically, but they didn't actually do it in the textbook. But a better way to do it is graphing this function on a calculator and finding the critical points. I got through all this and I ended up with this huge quadratic equation. I plugged it into the quadratic formula here. Maybe I made a mistake plugging it in somewhere. I don't know. But anyways, those are not the right answer. Let's actually graph it to see if we can get it that way. And here's what that graph looks like. So this blue one is the graph of that derivative. This is what I graphed right here. Let me click on it. There it is. So this is the graph of that derivative function, and it looks like it has the 0 right there, and that agrees with this graph. Whoops. This graph that we can see of the actual time function. It looks like it has a minimum here around 1400 or 1500 for x. And then we can't really see these on the same scale, so I have to zoom way in to see the other one here, the graph of the derivative. And the derivative here is crossing the x-axis. It's equal to 0 at about 1463 feet. That right there is the distance that you should walk before turning onto the field. So yeah, all of this did not work. There's a mistake in there somewhere. The minimum is at x equals about 1463 feet. And if you want to know what the actual time is, you can plug that back into the function, back into the original time function. So that problem is pretty difficult. Okay, so let's just do one practice problem because all of these problems are pretty tough. And by the way, there's going to be a second video for the section. It's a tough enough section with enough hard kinds of problems that I want to spend more time on it, and we'll have extra time in class to come up with these problems. So anyways, here's one that's not too bad. Let's say there's a rectangle with one side on the x-axis here. And then two vertices are on this curve. This curve here is a graph of, the black one is a graph of y equals 1 over 1 plus x squared. The maximum y coordinate is 1 there. So it looks kind of like a bell curve sort of thing. And this is the rectangle we're talking about. And we can tell that if x is too small, it's going to be very tall and narrow, or not even very tall, it's just going to be narrow if x is small. And then the wider that x gets, the smaller the height gets. And so it's hard to tell where it will be at its minimum and maximum. So you should try this. You're going to need to get a formula for the area of this in terms of x. So area equals something with x in it. and get the derivative of that. It's a little tricky, but you should do it. And the answers will appear in a few minutes, but I say in a few minutes because you're going to work on it on your own for a few minutes. And let's see the answers in 3, 2, 1. So I found the area function like this. It's the length times the width of this rectangle. The length is 2x. The width is the y coordinate of the thing. And anyways, you multiply them and you get this. I took the derivative of it to find critical points and got this thing. And the critical points are going to be where either the numerator of the derivative is equal to 0, or where the denominator is equal to 0. In this case, actually, this denominator is never 0 because x squared itself is always positive. So 1 plus x squared is always greater than 1, and so that's never 0. But the numerator can be 0, so I just solved this quadratic equation using the quadratic formula, and I got about 0.81. That is the value that x should be to make the derivative of this thing 0 here. So that happens at 0.81. But there's an important thing to consider here, which is, how do you know that this is actually the minimum? How do we know, or I'm sorry, the maximum? How do we know that the graph doesn't actually go up forever? Like, it kind of makes sense that you might want to make this box like wider and wider and wider forever to make the area larger and larger. Like, how do we know that it's going to get smaller? So to do that, you still need to think about the endpoints of the domain, and in this case, if the domain is all positive numbers, then that includes like as x approaches infinity. So what's happening all the way out to the right here? And in this case, if you take the limit of this area function as x approaches infinity, the x squared is going to be greater than the 2x. So this whole thing is going to get closer and closer to 0. So it's got an asymptote there. And you can also tell that if you plug in x equals 0 into this, you get 0 over 1. That would be, if that's not really a rectangle at all. So yeah, this should become 0. So that's that point, and then out here it gets closer to 0. And the only way this could have a critical point is if it is a maximum. Just trying to draw on what that graph has to look like there. So that is that does make the area the maximum. We could actually do, if we want to find the maximum area, plug that into this and see what it comes out to be. But that isn't quite the answer to the question, because it said find the vertices. So I guess that's going to be all 4 points. So once we know this x coordinate, it's pretty straightforward to find the other 4 points. Here they are. So this is really the answer to the question, what it's looking for. And so yeah, these problems are all hard. Pretty much all of them, at least all the interesting ones, are hard. They do take some struggle, and there's weird things to think about. You have to think about the domain, the endpoints of the domain. You got to draw pictures. Each one of these problems should take, as long as like 5 problems from other sections. So we are going to spend some time on it, and I'll see you in class on Thursday. Have a good Wednesday.